Hi everyone, in this video we're going to go through section 4.5, the dimension of a vector space, and we start out the section with two theorems, ultimately leading to what is a definition for dimension. Okay, so the first theorem, theorem 9, we're not going to do a proof of. We will do 10, because you know how much you love them. If a vector space V, actually let me highlighter here, if a vector space V has a basis, right, we've talked a lot about basis in this chapter, then any set containing more than n vectors. Now, n, the n vectors that's referenced here, is the number of vectors in my basis for my vector space. Any set containing more than n vectors must be linearly dependent. Pause the video if you need to. Think about that for a minute. Why, if I have a set containing more than n vectors, does it have to be linearly dependent? That one you should hopefully be able to grasp, but just to point out, my basis set is linearly independent by definition of basis. So if a set has more than that, more vectors than that, they have to be dependent. Okay, and then theorem 10, which we will do a proof of, if a vector space V has a basis with n vectors, then every basis must consist of exactly n vectors. Okay, so that's theorem 10. Any other basis for my vector space has to have the same number of vectors. Okay, and like I said, we are going to do a proof of theorem 10, so let's get rolling on that. Okay, so let me write out the proof. Let's see. So we're going to talk about two different bases. I'm not sure. We're going to talk about, we're going to say let B1, our first basis, let B1 be a basis of V with n vectors, and it's a terrible handwriting, sorry, and B2, another basis, be any other basis for V. I'm not going to write that, but any other basis of V, excuse me. And what we're going to show ultimately is that they have to have the same number of vectors. All right, and the way it's kind of a two-pronged argument. The first prong, if you will, is since B1, that basis, is a basis, and B2 is linearly independent. Since B1 is a basis and B2 is linearly independent, then that's a terrible B. Then B2 has no more than n vectors. Now, that is by theorem 9, the one above. If that theorem 9 made sense when you paused it and thought about it for a minute, B1 is a basis, B2 is linearly independent, B2 can't have any more than n vectors. It has to have less than or equal to n vectors. All right, now the second prong to the argument, where am I? There I am. Since B2 is a basis and B1 is linearly independent, then B2 has at least n vectors. Again, if you need to, pause the video, think about that for a minute. Why does that make sense? But then you put those two pieces together, that B2 has no more than n vectors and B2 has at least n vectors. If you combine no more than and at least, you get the conclusion of the proof. And we get to say it all formal and such. Let me go back to blue. Thus B2 has exactly n vectors. Boom. There's our proof. All right, now we get to the main definition in this section, and that is the definition for dimension. Okay, I'll read this one for you. If V is spanned by a finite set, V is said to be finite dimensional, and the dimension of V, when we write it with dim V, dim short for dimension, is the number of vectors in a basis for V. It's the number of vectors in its basis. The dimension of the zero vector space is defined to be 0. And then if V is not spanned by a finite set, V is said to be infinite dimensional. We'll be working with finite dimensional vector spaces, though, not infinite. Okay, so there's the main definition of the section. Now let's keep going here. The first example, when we have Rn, R2, R3, R4, the basis contains n vectors. So the dimension of Rn is n. Hopefully that makes sense. We use, as like, not even in linear algebra class, we talk about, two-dimensional objects, 3 dimensions, etc. We are in a 3-dimensional space, right? We exist in R3 that has 3 dimensions. That hopefully makes sense. When you write on a piece of paper, you are writing in a 2-dimensional space, right? We use dimension outside of linear algebra, and it means the same thing inside of linear algebra. We just kind of connect it to this term basis. And in the polynomial basis, the second part of this this example, the polynomial basis 1t squared, right? There's 3 vectors there. They are linearly independent. They span P2. That's polynomials up to a degree of 2. So the dimension of P2 is 3, right? Notice that number increases, right? Because the P2 is the largest degree, right? But we also include a degree of 0, so that's why that's always going to be 1 greater, whereas when we're talking about Rn, that is the same size. Hopefully that made sense. Okay, this next example, we're given a set H that is the span of those 2 vectors. The 2 vectors have 3 entries. So if there's 2 vectors with 3 entries, think for a second, what does that look like? What is the set H? H is a plane. H is a plane in R3. And how do I know it's a plane in R3? It doesn't have to be. It could just be a line in R3. But because the 2 vectors do not scale each other, right? We know that it's a plane. Or we know they're linearly independent, and therefore it is a plane. So a basis for H is the set V1, V2. Woo. Is the set V1, comma V2. Since they are not multiples of each other. That's kind of what I just said out loud. Not multiples of each other. And they are linearly independent. And are linearly, I'll abbreviate this, independent. So the dimension of H is 2. There are 2 vectors in a basis for H, so its dimension is 2. For this next example, right, we're given H is defined as this vector here for A, B, C, D, and R, right, and we need to find its dimension. And what we'll do is we'll take H and split it up into separate vectors. So we'll split it up into an A vector plus a B vector plus a C vector plus a D vector for A, B, C, D in R that are real numbers. Okay, and so what are the entries in my A vector? The coefficients are 1, 5, 0, 0. In my B vector, -3, 0, 1, 0. And my C vector looks like 6, 0, -2, 0. And the D vector is 0, 4, -1, 5. So hopefully you can see how H is the set of linear combinations of those 4 vectors. And so what we're going to do is we're going to take each of those vectors. We'll call V1 the first guy, the first 1, 5, 0, 0. And then V2 is the second one, -3, 0, 1, 0. V3 is 6, 0, -2, 0. I could have just gone right to this. That's a 0. But I wanted to just make sure that you could tell that H is the set of linear combinations of those vectors. And then V4 is my fourth vector, 0, 4, -1, and 5. And if you take a look for a minute at those 4 vectors and kind of investigate them, what you would notice is, whoops, that was supposed to be a highlighter. What you would notice is that those 2 vectors are scalars of each other. So I have 4 vectors in R4. However, they are not all linearly independent. So I cannot say that those 4 vectors are a basis for H. That would be incorrect. But we previously talked about the spanning set theorem. So we can say by the spanning set theorem, that was in 4.3. By the spanning set theorem, we're going to say we're going to discard, throw out V3. You could technically throw out V2 if you wanted to, but V3 is the bigger one. So we'll throw out that one. Then the set V1, comma V2, comma V4 is linearly independent and clearly spans H, so it's a basis. So the dimension of H is equal to 3 because there are 1, 2, 3 vectors in its basis. Now, in this next example, we're looking specifically at R3 and all of its subspaces. Okay, so we have R3 can have either a 0-dimensional subspace, a 1-dimensional subspace, a 2-dimensional subspace, or a 3-dimensional subspace. You can go from 0 up to 3. If it were R2, you'd only go 0 up to 2, R4, 0 up to 4, etc. So what is a 0-dimensional subspace? Well, that one's the pretty basic one. It's only the 0 subspace. Not very interesting, but, still, it's there. Okay, it's the subspace containing just the 0 vector. All right, and its dimension is 0. But a 1-dimensional subspace, that one's a little tiny bit more interesting. That is a subspace spanned by a single non-zero vector. Single non-zero vector. And not more importantly, but additionally, what does it look like? Because we're talking R3, we can conceptualize what these look like. It is a line through the origin. That's what a 1-dimensional subspace of R3 is. Okay, bumping it up then to a 2-dimensional subspace. This one is a subspace. Oops. Spanned by 2 linearly independent, abbreviating both of those, vectors. And what does that one look like? This looks like a plane, or planes through the origin. That is a 2-dimensional subspace of R3. It is a plane through the origin. And then a 3-dimensional subspace, move that down a little bit. This is 3 linearly independent vectors that span R3. And this, well, what does that look like? All of R3. All of our 3-dimensional space. Okay, so that's what all of the subspaces of R3 look like, contain, sorted by their dimension. This section includes 2 additional theorems, and there are proofs in the book. I'm not going to do them in this video because I try to keep it from going too long in these. But the first theorem is theorem 11, and we have H is a subspace of a finite dimensional vector space V. All right, that's just like the setup. Any linearly independent set in H can be expanded if necessary to a basis for H. So if I take any set contained within H, I can add vectors and I can expand it to be a basis for H. Also, if H is finite dimensional and its dimension is less than or equal to the dimension of its vector space. So, like, for example, if I'm talking about the vector space R3 and a subspace of it that looks like a plane, a linearly independent one vector can be expanded if necessary to be a basis for that plane. I can add another vector to generate the whole plane, and the dimension of that plane is less than or equal to the dimension of R3. That's kind of what's going on there. And then Theorem 12, the basis theorem, this one gets a name. V is a p-dimensional vector space, and p is greater than or equal to 1. Any linearly independent set of vectors, set of exactly p elements, in V is automatically a basis for V. So let me read that again. Any set of vectors with p elements is automatically a basis for V. Right? I know that it automatically has to be a basis because V is p-dimensional, and if they're linearly independent with p elements, has to be a basis. That's what that theorem says. And then the second part of it, any set of exactly p elements that spans V, also automatically a basis. Basically means if I get one, linearly independent or spanning, and it contains the right number of vectors, I don't need to check the other one. If it's linearly independent, has to span is a basis. If it spans, has to be linearly independent. It's a basis. That's what that one says. And now we get to our final example of this section where we need to find the dimensions of the null space and the column space of this matrix A here. And just to briefly put it up here, the column space of A, its dimension is the number of pivot columns. And then the null space of A, its dimension is the number of free variables. And to answer both of those questions, what do we need? We need reduced row echelon. Actually, no, I take that back. You only need row echelon form. It does not have to be reduced. Oh, that saves a little bit of work. Actually, if you use your calculator, it doesn't save any work. But let me write down what I'm going to do here. Oh, we're going to take the matrix A, augment it with a column of zeros, do some row reduction. We want it in echelon form. 1, 0, 0, minus 2, 0, 0, 2, 1, 0, 3, 2, 0, minus 1, minus 2, 0, and then my column of zeros because I'm augmenting this with zeros. Okay, feel free to check that one in your calculator, but I did, so hopefully that's okay. Okay, so now what are the two dimensions to answer the question? The dimension of null A, the dimension of the null space is 3. How do I know it's 3? Because I have 1 free variable, 2 free variable, 3 free variable. Right there. 1, 2, 3. Those are my missing pivots. And then the dimension of the column space of A is equal to 2 because I have 1 pivot column, 2 pivot columns. 1 there, 1 there. So there's 2 pivot columns. The dimension of the column space is 2. All right, that is the end of this section. Thank you for listening. Don't forget to ask questions as you have them.